Polynomial functions are the sums and differences of monomial functions that form other types of polynomials. Let me show you an example. This is an example of a polynomial. So each one of these is identified as a monomial, and they're joined together in a string of sums and differences. So we have subtraction sign, an addition sign, and another subtraction sign. Together, this is a polynomial. Notice that we always set them up in decreasing exponents. So the 4 is furthest to the left. We don't have an exponent of 3, and that's okay. It skips to 2, and then 1, and then a constant. That is standard form for a polynomial, from increasing on the far left to decreasing on the far right, when we're talking about our exponents. The number of terms are the number of monomials. So we have 1, 2, 3, 4 terms in this example. The leading coefficient is always paired with the highest exponent. So in this example, our leading coefficient is 3. The degree is the highest exponent in the polynomial. So in this case, the degree is equal to 4. You will be asked to identify the number of terms, the leading coefficient, and the degree of a polynomial. We're also going to use this information to talk about end behavior, something that we discussed in the previous chapter. We are going to express our end behavior using limit notation. Let's go over a couple of general rules of end behavior. Remember, end behavior talks about what's happening on the far left and far right-hand side of a graph. It ignores what's happening in the middle. So we're going to go through 4 different scenarios. We can have end behavior going up on the far left as well as the far right, going down on the far left and far right, and then alternating up, down, and down, up. Now there are significant characteristics in the equation of the polynomial that lead to this specific end behavior. In the first example, if we have up, up, that means that our degree is going to be an even number and that our leading coefficient is going to be positive. So same direction of end behavior means even. The reason why the leading coefficient is positive because we do not have a reflection in the x-axis. If we are going down and down, that means that the degree is also going to be even, and the leading coefficient will be negative, meaning that there's a reflection over the x. If our end behavior is going in 2 opposite directions, then that means our degree is going to be odd. And if our leading coefficient is negative, then it's going to go up on the left-hand side and down on the right-hand side. And for our last example, again, we have an odd degree, and this time our leading coefficient is going to be positive. So we're going to use that information to find the end behavior of this polynomial. The first thing we want to do is we want to make sure it's in standard form. That means that the highest exponent needs to be furthest to the left. So I'm going to rearrange these. I have negative 8x cubed should be in the first position, then plus 4x squared, then plus 20. Why it's important to rearrange these is so we identify the leading coefficient and the degree properly. So my leading coefficient is negative 8, my degree is 3. The degree of 3 is an odd degree, and a leading coefficient of -8 is negative. So if we look at our chart, we're looking at odd and negative. Up on the left-hand side, down on the right-hand side. So we actually don't need to graph this to identify the end behavior. So I'm going to do a little visual that's going to help me put together the end behavior. Up on the left, down on the right. As x approaches negative infinity, so that's what's happening on the left-hand side, of g of x is equal to, so on the left-hand side, the y values are getting bigger. So we go towards positive infinity. Then I have to say what's happening on the right-hand side. As x approaches infinity, positive infinity of g of x. So I look at what's happening on the right-hand side. On the right-hand side, the y values are getting smaller. So I'm going to write is equal to negative infinity.